Welcome back. This is LTC 09 in our long-term care predictability series. Today, we're talking about MEP reliability and redundancy. MEP stands for mechanical, electrical, and plumbing systems. In plain language, these are the systems that keep the building operating: the heating, the cooling, the ventilation, the power, the water, hot water, alarms, controls, low voltage systems like your key card controls, and other building infrastructure. The risk is this: when teams value engineer these systems only for first cost, they can accidentally create daily operational problems for staff, residents, patients, and facilities teams. So today, I'm going to give you a one-page tool to test the MEP decisions before a short-term savings becomes a long-term operating problem. This is for operators, CFOs, facility directors, clinical leaders, development teams, engineers, and GC or construction management partners. The stakes are direct. If MEP reliability is underdesigned, the facility may face avoidable outages, room comfort issues, humidity or ventilation problems, hot water disruptions, nurse call or low voltage failures, alarms that do not support real response, or maintenance access that requires major disruption. In long-term care, these are not just technical problems. They affect operations, safety, compliance confidence, staff workload, and resident or patient experience. Here's the predictable failure pattern. A value engineering item is proposed. It saves money on the front end. The team accepts it because the drawing still works and the budget gets relief. But no one fully tests the operational consequence. Later, facilities discovers that the system is harder to maintain. Clinical leadership discovers the outage tolerance is lower than assumed, and staff discover the workaround. The owner discovers that a small savings created a recurring operational exposure. The issue is not value engineering itself. The issue is value engineering without an operational risk filter. MEP reliability means the building systems that support care delivery without requiring fragile workarounds. It does not mean every system must be oversized. It does not mean every system must have full redundancy. Redundancy means backup capacity or an alternate way to keep a critical function operating. The right level depends on the care model, acuity, resident or patient risk, staff model, existing building conditions, code requirements, and owner tolerance for downtime. But the decision should be intentional. The dangerous version is when reliability is reduced by accident because the team only looked at first costs. Value engineering should mean improving value, but all too often it gets used to mean cost cutting. These are not the same thing. Good value engineering asks, can we reduce costs while protecting the outcome? Bad value engineering asks only, can we reduce the line item? In long-term care, a cost cut can transfer burden to operations. It may save money in construction, but create maintenance problems, staff workarounds, comfort complaints, downtime exposure, or risk during occupied renovations. So the question is not just, what does this save? The better question is, what operational risk are we buying? The tool for today is the MRRC, or the MEP Reliability and Redundancy Canvas. The purpose is simple. Before you accept an MEP decision, substitution, or value engineering proposal, test what it changes operationally. The worksheet walks through critical systems, operational dependencies, reliability risks, value engineering impacts, redundancy choices, shutdown planning, and temporary service needs, commissioning, and a go or no-go gate. This is not engineering advice. It's an owner and operator decision tool that helps you ask better questions to your engineers, your contractors, your facilities team, and any authorities having a jurisdiction. Step 1 is the critical systems baseline. List the systems that directly affect care, delivery, and continuity. Electrical and emergency power, HVAC and ventilation, domestic water and hot water, plumbing and sanitary systems, fire alarm and sprinkler interfaces, low voltage systems like your nurse call, your access control, your security, and your communication, controls, and building automation. Then for each system, ask, what operation depends on this? What happens if it fails? What is the criticality? High, medium, or low? And who owns the next confirmation? This step prevents the team from treating all MEP scope as equal. Step 2 is the operations dependency map. This is where we translate technical systems into real facility operations. For example, med storage and med pass may depend on power, cooling, lighting, access control, and communications. Meals and dining may depend on power, water, waste, ventilation, and equipment. Bathing depends on hot water, drainage, exhaust, room comfort, and staff access. Resident room comfort depends on heating, cooling, ventilation, controls, and maintenance response. Security and elopement control may depend on low voltage, door hardware, alarms, power, and staff notification. The point is simple. If the system fails, what part of operations fails with it? Step 3 is the reliability risk test. This is where the team looks for single points of failure. A single point of failure is when one item that can stop a critical function if it fails. Ask, can this system be maintained without major care disruption? Are alarms, monitoring, and responsibilities clear? Are critical rooms protected against overheating, underheating, water loss, or exhaust failure? Are equipment access, replacement paths, and parts lead times understood? Are outage durations known? Are temporary services possible? Are commissionings and startup expectations clear? Reliability is not just the equipment. Reliability is the whole support chain around the equipment. Step 4 is the value engineering impact filter. Every proposed substitution or cost reduction, write the first cost savings. Then write the operation affected. Then write the risk created. Then decide, do we accept, do we mitigate, or do we reject? This is the discipline that keeps value engineering honest. A less expensive unit may be acceptable if the maintenance access is still good, the performance is still appropriate, and parts are available, and the downtime risk is manageable. But a less expensive option may be a bad decision if it creates a single point of failure, increases staff burden, creates comfort risk, or makes failure replacement disruptive. Savings are only savings if the outcome still holds. Step 5 is the redundancy and backup strategy. Not every system needs a full redundancy. Full redundancy can be expensive and it may not be justified, but every critical system needs an intentional strategy. Maybe the answer is full backup. Maybe it's partial backup. Maybe it's a temporary connection point, and maybe it's a manual workaround that leadership accepts. Maybe it's a phased replacement plan, or maybe it's a no-go because the downside risk is too high. The important thing is that the strategy is explicit. When redundancy is not discussed, The project may accidentally choose no backup without anyone realizing it. Step 6 is the shutdown, the temporary service, and the commissioning plan. This matters, especially in renovations and occupied facilities. If a system has to be shut down, tied in, replaced, tested, balanced, or recommissioned, the operation plan needs to be clear. Who's affected? How long is the outage? What temporary service is needed? How are staff notified? How are residents, patients, and families informed? What testing happens before the system is turned over? Who confirms that the system is ready? A system is not ready just because it's installed. It's ready when it has been tested, understood, and accepted into operations. Here's a common scenario. A project team considers a mechanical reduction cost. On paper, the system still meets a target, but the team hasn't tested how the change affects resident room comfort, high acuity areas, staff response, maintenance access controls, or future service. In a care setting, comfort complaints aren't minor. They can affect sleep, agitation, staff workload, family confidence, and operational response. The right answer may still be the lower cost option, but it should be accepted only after the team understands what's changing and who's responsible for managing that risk. Another common scenario is treating low voltage systems as small scope items. Nurse call, access control, security, cameras, communication systems, door interfaces, and monitoring tools may not look like the biggest cost lines, but they strongly affect staff response and safety. If the value engineering decision reduces coverages, creates alarm fatigue, limits future expansion, or weakens staff notification, it can only create daily operational friction. In long-term care, low voltage design is not just technology, it's part of the care response system. Now we want to use the go or no-go gate. A decision is a go only if the critical systems and the operational dependencies are mapped. Single points of failure are identified, downtime tolerance and temporary service plans are documented, maintenance access and replacement paths are confirmed, alarms and controls are clear, commissioning requirements are defined, and the AHJ and compliance confirmations are assigned. Value engineering savings have been weighted against the operational risk, and open risks have an owner, a due date, and a decision path. If an open MEP issue could change the layout system, scope, cost, phasing, commissions, or operational continuity, it's a no-go until that issue is resolved. So let's recap. MEP decisions are not just technical decisions. They're operating decisions. The MRRC worksheet helps you connect systems to operations, identify reliability risks, test value engineering proposals, choose backup strategies intentionally, and avoid accepting savings that create hidden operating costs. In the next video, we'll move from systems to budget control and look at the cost drivers that owners underestimate every time. Download the MRRC worksheet from the Arete LTC tools page, and we'll see you in the next video. If there's one question to take from this video, it's this. Do not ask only, how much does this save? Ask, what risks are we buying when we cut this? In long-term care, a cheaper system is only a better system if the building still supports care, staff, compliance, and continuity. That is the predictability standard. Hey, before you go, I want you to walk around your facility this week asking one question. What is the lesson that this space is teaching? The doorstops, the supplies at the nurse's station, the empty logbook that everybody walks past, the staff walking the long way around, and the families asking for directions. These aren't random. They're the lessons that the space has been teaching every day, every shift. Your staff didn't create that friction out of nowhere. And another reminder probably won't fix it. The facility friction roadmap lets you see your building the way that your staff are experiencing it. It shows you what spaces are teaching inefficiency, which are teaching workarounds, and gives you a practical place to start changing the lesson. It takes about 4 minutes. The link is in the description. Take the roadmap and find out what your spaces are teaching.